I wanted to begin by expressing gratitude and thankfulness to our igniters for such fascinating talks. I think they did an incredible job of addressing the question of the quantum information structure of space-time so directly and in such different, diverse ways. So I think we have an opportunity to discuss a lot of very different ideas now. This is just a framing, and they may very well disagree with what I'm about to say, but for me, they sharpened a practical question in doing quantum gravity. In classical general relativity, we have this interesting split. We understand now that coordinates have no physical significance, that the fields carry the physics, the fields over our coordinate systems. But in the classical theory, it's an immensely practical thing to be able to change coordinates, to label points with these meaningless labels, but that we can use as practical tools to do computations. So each of them offered sort of different perspectives, both on the quantum information structure and on the practical tool side. And so I'll summarize my thoughts on those things and open the floor to discussion. So several of them focused on entanglement structure as a way to try to characterize space-time regions, this question we've been thinking deeply about, of how do I split space-time into sub-regions. And Eugenio brought in the entanglement as a way to even characterize, rather than using our old variational notions of sort of reducing the energy of a physical system, can we use entanglement as a way to pick out the semi-classical states, the low energy states, if you will, of the theory. Within that, the practical tool he introduced was these subalgebras of observables. So can we use those to identify our physical system? Rob bring in that same perspective, that perspective of entanglement as subregion identifying, but with a very different set of practical tools, using this dictionary of holography to connect sort of classic information theoretic tools on the conformal field theory side to a different set of variational problems on the geometrical side, the variation of extremization of the area. Pablo, and this is why I use this framing, Pablo had a very, very different approach, a very complementary approach, which was to sort of introduce a quantum version of labels, labeling our tensor product decomposition, our structure decomposition, with more information in the labels themselves of both the subspaces and of the kind of tensor product that we're talking about, and brought in the question of whether we can talk about limited speed of information and things like this by using this richer set of quantum structured tensor products. And Hakim brought in this interesting perspective of, well, information has the opportunity available to us of sort of making consistent a discrete and a continuous perspective on space-time, and doing that through correlators and through thinking about the correlators as the practical tool to do this. So I think this is a very interesting opportunity for people to express both encouragement for the different programs and hesitations about the different programs. And so I'll open the floor now to questions. We'll use the same strategy we've been using, with a finger as a continuation and a hand as opening a new subject. Let's begin back here.
Thank you. I'm Nisetu from Oxford, and I wanted to make some comments on the connection between what Pablo and Eugenio said. So first, we have been doing some work on these subalgebra observables, and we have been doing some work on a special type of system which is called anionic systems, which have a structure that resembles what Pablo was presenting. So a question to him would be, have you studied these graphs and these fusions in terms of fusion categories or any connection to anionic systems? And have you studied the algebra of observables there?
Pablo, would you like to respond?
Thanks. So what we are currently trying to do is to establish a connection between this generalized tensor product and the Feynman algebra approach that Eugenio was following of understanding through the Artin-Wedderburn theorem subsystems as direct sums of tensor products. We haven't been looking at fermions and anyons in that context.
Daniele?
Yeah, I wanted to ask you the opinion and get a suggestion from everyone about an aspect of the information gravity or information space-time story that has been only barely touched in the talks, which is how to reconstruct the dynamics of space-time and the Einstein's equations. Most of these reconstructions have been at the kinematical level about reconstructing a manifold or a metric and so on, but where does the Einstein's equations or a modification thereof come from? And I want to hear suggestions about the direct link between, or a definition of the dynamics of information in some sense, and the Einstein's equations. Or maybe as a possibility could be that there is an intermediate step which is reconstructing from information thermodynamics, and then run the algorithm by Jacobson or others to then go from thermodynamics to the Einstein's equations.
I think Lee has a response. Hold on just a sec, Lee. We'll bring you a mic. Ah, great.
I want to commend you for that remark because it's been one that's been needing to be made here. To me, physics is about energy and energetics, as well as about information. And the most cherished result we have in the whole history of quantum gravity, in my opinion, is this result that you just mentioned by Ted Jacobson from 1995. And what Ted's result tells us, very simply, is that there is a flux of information, and there is a flux of energy, and they're equal.
Other follow-ups on this theme? Rob?
So I didn't talk about it today, but it is, I guess, related to energy, but there's what we now call a first law of entanglement, which is looking at perturbations of the entanglement if you add extra energy into the subregion. And in the holographic setup that I talked about, you can actually show that, well, if I can evaluate all of the entanglements in the boundary, then the bulk theory must be a solution of Einstein's equations. Although that's a bit over the top in that what you're really showing is that the perturbations satisfy the linearized Einstein equations around the vacuum state. You can go further than that, but in our current way of thinking, it's just becomes a very laborious thing to get nonlinear terms in the Einstein equations. But I think that also inspired Ted for the version 2.0 of his derivation of Einstein's equations. It's very similar to the kinds of calculations that we do in anti-de Sitter space. But it really is very closely connected to ideas of energy that Lee was referring to there.
I have Lynching and Carlo. Lynching.
Thank you. I have a question for Rob. So recent couple of years, there has been a very beautiful work by Sovet Raju on challenging the quantum extremal island paradigm. And so he pushed the holography a bit even further to say that all the information is localized on the boundary for the asymptotic flat space-time, and hence the page curve should be flat. And also, in the typical quantum extremal island calculation, there's a reservoir on the boundary, hence this gives a effective mass for the graviton. And so I want to ask you about what's the current stage of understanding from Raju's challenge what the quantum Dremel Island calculation really says about the black hole information paradox. Thank you.
I am really fascinated by Subrat's work. I think it's really important, and I have to confess that I don't, fully understand all of the calculations there. So the one thing that I would say about it, which is more, I present it as an observation, not a criticism, is that it really, the protocols and the approaches that they're using are very much like standard quantum protocols, but what that requires is that you prepare the state many times and you measure it many times. And so in his context, what that means is I'm preparing a new universe or a state of a universe many times and then sampling it. And so it becomes sort of, quantum gravity is very much an in-principle thing, but it's sort of observations that meta-observers could make, people who have access not just to our universe, but people who have access to this whole ensemble of universes. Again, that's not a criticism, it's more an observation of the kind of work that I certainly hadn't appreciated until very recently about their construction. But beyond that, I'll just say that to me, I find it a fascinating set of ideas, and I don't have a proper response to your question.
Laurent has a follow-up.
Maybe it's for Rob, but also for Eugenio, because in some sense, and that has been part of the discussion so far, as you're saying, in fact, as you show very clearly, the existence of the page curve is just tied up with this factorizability of the Hilbert space, which we know is, the things that has to give up in quantum gravity, which is in fact the reason why holography could work, or is working. Eugenio, I wanted to, in some sense, it's just a logical fallacy as a, let's say, philosopher. You make an hypothesis, you get a result. This hypothesis is wrong. Why do we still believe that we should use this page curve? And in some sense, this is the essence, besides the remark of Rob, this is the essence of Raju. It's very simple. It's just pointing out that there's an hypothesis in the derivation of the page curve, which is simply not true. And it's as simple as that. So why do we continue to use a result which we know doesn't follow from our hypothesis?
Eugenio, Hakim, and Carlo.
Ron, thanks for bringing that up. I completely agree. The original page curve requires a notion of tensor product and of finite dimensional Hilbert space too. Now the question is, when you don't have that structure, can you still make sense of the page curve? And one thing that I was illustrating earlier is that there is a notion, it's not immediate. You first of all have to identify these subalgebras of observables that have to satisfy some properties. As you know, the subalgebra of observables is type 3, you still have a problem. So the question is, are we speaking about subalgebras that are physically relevant, that correspond to measurements, for instance, for a black hole evaporating? Are we speaking about detectors that you put far away from the black hole, and speaking only about the entanglement of all of the measurements of those detectors with everything else? But once you do that, then there is a formula for doing that. You just have to consider these structures where you don't have a tensor product. The modification is quite simple. It's just a direct sum of tensor products. And that is something one can use. And the concrete example that I was giving is in condensed matter theory, typical states at fixed energy. You don't have a naive notion of page curve, but you have this more sophisticated and operational notion of a page curve.
Can I just have a remark on that? Because, so I agree if you have this direct sum, but in general, it's more complicated. So you only have a direct sum of tensor product to the entanglement if the surface algebra is commutative. So in general, if it's not commutative, and this is kind of the essence of the work we did with William, what you have is what you have to share is just the label of the representation. What you have to share is this infinite dimensional representation of this non-commutative algebra. So I think the mistake there is to to continue to treat gravity as the linearized version. Of course, in linear gravity, all these algebras are commutative, but the true nature of this holography, when it comes, you take that non-commutativity into action, and then, anyway, you know, the level of entanglement to the boundary degrees of phenomenon to the bulk due through this non-commutativity is much stronger, and you cannot go through that argument. So I would push you back that, you know, you need to use a fusion product, not just simply.
I expect that we are speaking about the same structure in a different language. You were saying a non-commutativity and there's some label to sum over. So I'm arguing that this non-commutativity is the one that leads you up to a center. And when you diagonalize that center, you have a sum over the eigenvalues of your operators in the center. And that's the direct sum that I have. So I would say if we take the same system, but we treat it in these two different languages that we are using, I expect we are going to get the same notion, physical notion in the end. So in that sense, it's not a tensor product, it's a direct sum of tensor products, and I expect that this is the same structure that you are also using when you are non-commutativity. This direct sum is coming from the non-commutativity. It's the fact that my subalgebra and the rest still have a center.
Okay, we could I agree, but this notion of diagonalizing a non-commutative algebra is non-trivial. By definition, you cannot really diagonal. That's the whole point. So there's all of this, anyway, you know, reservoir of degrees of freedom, which are the diagonalization. You can only access the Casimirs of the algebra, and then you know you have these reservoirs of states, which are really where the true entanglement go through. And I think things like U1 or linearized gravity could be misleading in that factor, but we can exchange more.
Akim had a follow-up, Carlo had a follow-up, and then we'll...
Thank you. Coming back to the original question, which was, if I understand correctly, what connections one could draw between information theory on one hand and the dynamics of space-time, the Einstein equations. And I would like to just point attention to spectral geometry here. There are many results that show that in some expansion, the Einstein action arises naturally. For example, there is a result by Gilkey that was pointed out by Hawking, which is that the number of eigenvalues of a wave operator below a threshold in the Euclidean signature case has an expansion that starts out with a cosmological constant, and then the Einstein action and higher order terms that are highly suppressed. And the number of eigenvalues below a threshold, that's something that naturally arises if you describe actions information theoretically. So I think that's one possible avenue one might consider, how information theory could link to the dynamics and of space-time and to how the Einstein action might arise.
Carlo? This is the, is this the follow-up or the hand? The hand, okay, and that's fine. You're next.
Okay, so I want to change the topic and, I mean, at least partly change the topic. Because there were all sorts of interesting ideas this morning, but there's one main question that Akim has put on the table, which is, I think is very good, and we can think of the relation between problem of quantum gravity, problem of quantum information in two terms. Either quantum information is a tool, is a very large tool that we can use, or the alternative, which is tempting, is to take information as fundamental, sort of try to use it in a fundamental way. And we have heard a number of it's on the table. Jacobson is one of the hints in that direction. And I want to say what my attitude with respect to that. I grew up under the spell of John Wheeler, of course. I mean, because I mean it's hard to resist his spell when you interact with him, and his it from bit. And my 96 work on relational quantum mechanics is the derivation of quantum mechanics from informational postulates. Was very much under the hope of say, can we use information as a starting notion out of which build something else? 30 years have passed, and I think the opposite way today. In the following sense, I think that information is an extraordinarily powerful tool because since both generativity and quantum theory force us to talk in this relational way for very different reasons, we're always in some sense talking the information that some observer or some part of space-time has about another observer, another system, another part of space-time. So obviously, as soon as we define our basic stuff of the world, we can talk about the information as I think the cleanest, most large and basic notion of information is not the one in Shannon in the first page, but the one immediately after, which is relational, relative information. You have two systems with a constraint, and you can define information as the fact that there is a constraint. So the number of total states is less than the number of the product of the number of states of each, and you can quantify this by sort of log of the number of states of both minus, so the log of them say one plus the other minus both. So as soon as you have variables and dynamics and constraints, you have information. But it's not the way around. The other way around doesn't work, in my opinion. And it has never worked, it never got any way. It has fascinated a lot of people and stays there. So I think it's useful to view information as one of the most widely available tools for thinking about the fundamental stuff, but a tool for thinking about the fundamental stuff, not at the fundamental stuff. And there's been it seems to me that the current discussion is parallel to what happened with energy at the sort of late 19th century or whatever, when there was this energetic, people got enthusiastic, especially in some countries, in Germany and some that world, say, okay, we got it. The universe is just energy, and the rest is, and you know, with general relativity, the universe is not just energy. Period. It's just there's no energy conservation in that sense. You have to have fields with properties, a variable with properties. You have to have stuff, and then in some cases you can define energy appropriately, and it's super useful because every time you have a time translation invariance, some kind, bingo, energy becomes a. And every time you have two systems interacting, bingo, energy is it's the right quantifying tool. And I think this is also important for trying to make sense of this fantastic result by Ted Jacobson, which I think it's super good if you interpret correctly, but it would be horrendously misleading. And it has been misleading for a long time. Misleading is that try to interpret it as a hint that sort of gravity is due to some entropic elastic, like elasticity, some entropic phenomena. That has not led anywhere, it's not leading anywhere, and it's wrong. It's just wrong, because if you go into detail of the derivation, what comes in, it's a very specific mechanical input. I'm not going into detail, or maybe I should. The entropy, at some point, there's assumption that the entropy is proportional to the area of the entropy of something is proportional to the area of something. And this is put an input, but the proportionality constant is assumed to be independent from the state of the things around. And the entropy is always proportional to the entropy in similar situation, but with a proportionality constant which depend on the state. It's this independence which is the core of the ingredient of Jacobson derivation. And once you see where it comes from the sort of the background, the general covariant symmetries of the theory. So the ingredients that is going on there is not informational. It's of a different kind. And finally, and I close. This come over and over. Akim tell us, look, I mean, you take the 2-point function, take the two derivatives, and bingo, you get the metric. Wow! So I get the metric out of the 2-point function. And then you think about it, and say, well, of course, I mean, 2-point function is something you compute out of the dynamics, the Lagrangian. The Lagrangian is the metric, so of course you can, in the solution of the equation of motion, there is written down the metric, because it's one of the ingredients that come in. You can just extract it from it. How can we get the metric out of correlators? It's a beautiful suggestion but not by taking derivatives, because this works only if you put them in. You get the metric if you interpret what correlators are talking about as the geometrical quantity described by the theory. In other words, I don't think, and maybe I'm going too long, I don't think that it's useful to hope and continue hoping for decades after decades that magically out of information we get physics. I think it's the other way around. We need physics, namely some stuff which can be quanta of the gravitational field, or maybe it can be other. And as soon as we look at them in informational terms, we can do fantastic stuff with these tools, but not the other way around. So that's my position, which is the opposite of what I had 30 years ago.
You want to react, Kim?
Well, yes, in a sense, you can say that if you have the two-point correlator and you reconstruct the metric, you have to know that there is a metric to start with. But on the other hand, it could be that, the notion of correlator makes sense even when the notion of metric doesn't. I mean, the notion of a classical metric. And then what you have is that the metric is the derived quantity and the correlator is the primary one. And it's just that sometimes you don't have a classical space-time, you don't have a classical metric, but it's all still described by the correlators.
Lee has a
Yeah,
reaction.
oh, sorry.
You also? We'll do Lee and then Carla.
In response to all of these discussions about information and energy, think of the Hamilton-Jacobi equation, which is an energy. And think about making a probabilistic version of that, where you integrate that Hamilton-Jacobi equation against the probability density. And then consider that's a statistical distribution of an ensemble of particles satisfying dynamics given by the specification of energy. Take its canonical structure, and you see that some notion of probability is conjugate to energy. And I believe strongly that that's the beginning of a trace into, let's say, a mind that has much, much, much to reward us. And let me just say what the next step is. The next step is that in the canonical commutation relations, or in the first term of that action, you have integral rho E dot. And so you have three things. E, rho, and d by dt. You all know that we quantum gravity people are very fond of saying that time should not be fixed background. To take that d by dt and find a way to make it dynamical. Then you have not two things, not a duality, as in the usual conjugate duality, but a triality, where going from the duality to a triality is the essential step of making a theory background independent. And also brings in algebras that have to do with quantum.
Pablo, I didn't understand. Is yours a follow-up or a new question? Follow-up? Yeah, Pablo was before you said, sorry, Carla.
Okay, so there was a question about how to recover the Einstein field equations, but the way they are mathematically constructed are as so if you take the action formulation, there is a single scalar that's covariance, right? So you could hope that symmetries like covariance would then point you towards the right dynamics. And in that sense, I would like to ask a question to Achim Kempf, because at some point my hopes for obtaining covariance in discrete systems lied in this sampling theorem that you are using, because when you sample a continuous function, you can sample it in many different ways. And at the end of the day, you will reconstruct just the same precise continuous function. And so I was hoping that we could understand discrete covariance as different resampling of the same continuous function. Now, I was a bit disappointed though when I tried to follow that route, because when you try to compute a resampling of a fixed function, that computation is non-local. You seem to need to reconstruct the whole global continuous function before you can resample it. And so it doesn't seem to lend itself to just moves that characterize covariance. So that's my question is whether you have ideas on that, Hakim.
Reaction?
Could you just repeat again what exactly it was that you wanted to achieve?
Can we bring the other
Do we
mic
have to
over?
move the microphone again?
Right. So if I take a smooth manifold and I discretize it, there are many ways to discretize it.
Yeah.
And that, in a sense, could be the key to understanding an important symmetry, which is covariance. How do you go from one discretization to another? Now, I had hopes that we could make this formal by using your tools, your way of reconstructing a manifold from its discretization, knowing that there is some limited bandwidth and so on. And so that could make formal that two discretizations lead to the same geometry, right? However, it seems that this act of resampling a continuous function is not a local thing, not a local move.
Yes, that's right. So we agree that you can do it, but it's non-local in that sense, right? Yes. Now the non-locality is at the cutoff scale. And so basically what we have is diffeomorphism invariance, but it becomes non-local when you get down to that scale. And then you can speculate, what does that mean? What happens there? And I don't know either, but I think there are possibilities that are quite interesting. For example, if we have a band limitation in space-time in that sense, then we are literally throwing away degrees of freedom, all wavelengths that would be too short. And one possibility is that they sort of resurface, because what does it mean that we throw away wavelengths that are shorter than a certain threshold? It means that we can't resolve distances to arbitrarily small resolution. And it's conceivable that what used to be diffeomorphism invariance, for those degrees of freedom that we throw away, would resurface as a gauge invariance. You see, when you take a gauge field, then you can choose your gauge whichever way you want, and it doesn't usually, we don't usually attach any meaning to that. The isospinor vector could point in any direction in its isospinor space, and it doesn't have any meaning. That's part of the gauge principle. But it could be that this direction that it's pointing to is basically the remaining resolution between the cutoff and absolute resolution. It's basically the isospin vector would tell us where something is once we get down to the fuzzy scale there. Basically, the lack of diffeomorphism invariance at that small scale that you're talking about could be perhaps identified with the gauge principle. Now that's super speculative. I wrote one paper on it, and then I got stuck. So I can't really claim that this is the way to go, but I just want to say, yes, I agree, it's very interesting, and that non-locality, which is confined to just this tiny scale, means on one hand, I can't resolve that distance, and maybe that is another statement of I can't decide which gauge is the right one, right? So the ambiguity of which gauge you want to choose, the freedom that you have, could be the non-resolvability of distances smaller than the cutoff. But it's just super speculative. You might be completely wrong.
Carlo had a follow-up. I'll put you in the queue.
Yeah, I want to continue, but this is also related to the last thing being said, and I think the clearest way to say what I wanted to think is that Akim, you said that you have this super speculative idea, but in loop quantum gravity, you can express the theory in terms of correlators. So it's exact. There was a misunderstanding in previous exchange. I was not criticizing what you were saying. I was appreciating it. You can loop quantum gravity is a concrete theory, not a speculative idea. It might be wrong, of course, or might be missing pieces of it, but it's a concrete theory in which there are concretely defined. The theory is defined by a set of correlators. Okay, these correlators, transition amplitudes, if you want. These transition amplitudes are not in space-time in any sense. It's not an X and T when they're sitting. And in the very precise sense, space-time comes out of it. And in a very precise sense, there is discreteness. And in a very precise sense, there is general covariant invariance and symmetry. And if you, to the extent that we were able to write states which at large scale look like continuous space-time, at short scale there's discrete and the Planck scale, but in a quantum way that doesn't break the general covariance at all, precisely because it's not written into a space-time, but space-time is things that emerge into it. So it is a case in which you can, right or wrong, it is a case in which you can express the full theory in terms of these correlators, and that's why I think yes. So it's a correlation between things that makes up the merge all the rest, and that's why information-theoretical terms are useful. The but was, but it's not that one starts from information-theoretical things and builds up a theory. The theory was built up starting from a stuff being the gravitational field quanta, okay, which has some properties which are clearly analyzed, and the same is also true the spectral action that you mentioned. It's true that there is this beautiful result by Kohn and forgot his collaborator, that you can write the Hilbert action plus corrections, just as the number of the Euclidean actually, and the number of eigenstates something below. But once again, you can perhaps view this in quantum information terms, but you have a specific object, a specific dynamics, a specific Lagrangian, and then you analyze it in information terms. That's what I was trying to say.
Lee had a follow-up.
Theories, infinite dimensional gauge theories, onto diffeomorphism learning theories and back. And the intermediate step in the demonstration of that are a certain class of cubic matrix models. And as I think Akim you appreciate, the delicate issues are ones of measure and how you put measure on the matrix elements, why you deal with infinite matrices. But just to be provocative, the other step we jump over these equivalences is a computer machine, in other words, a machine learning device, which we take to infinite dimensions. So there's a lot, in my opinion, to look at in those things, but they're very subtle.
Daniele, I understood you had both a follow-up and a new. Can you just do the follow-up now? Behind you.
It was a follow-up about the issue of reconstructing the Hansen's equations from quantum information.
Okay.
That was mentioned. So I fully agree that general covariance or diffeomorphism invariance will be the crucial ingredient. On this, however, I have two comments. One is that exactly diffeoinvariance will suggest that what we should try to do is not to reconstruct a space-time manifold with a metric and so on, because that's exactly the redundant way of formulating the dynamics. I would suggest that we should rather try to extract directly a dynamics in terms of relational observables, in which diffeomorphism invariance has been already taken into account. That's the first comment. And the second is that, however crucial is diffeomorphism invariance, is not, I mean, it will not select the Einstein's equations uniquely. You can write down many actions, many equations for a metric that are diffeomorphism invariant. And so we also have to keep the eye open for looking for what could be the extra ingredient that would really select the Einstein dynamics over something else.
Francesca had a new finger from before? Okay, no problem. Then Daniela, go ahead with your new theme. Did you have a new one as well? No? Great, then it's Laurent.
Yeah, I want to come back to the question of linking about, about the dynamics, I think, but maybe with a different twist. Because so far only Rob kind of really gave a concrete, example of how you would get, from an informational perspective, some kind of dynamics. And this example is around static. So I would like to challenge the other speaker to maybe go beyond that. But also I would like to ask, so one thing which is special about GR, and about the dynamics in the context of GR, is that if you take any object, any charged object, any massive object, and you move it, it will emit gravitational radiation. And this gravitational radiation will carry itself energy and information. So to precise the questions of understanding the dynamics, there's something that you need to do a little bit before, is to give me your information theoretical context, or what you would call gravitational radiation. So, right, if I want to play this game, which I do, in fact, I do want to play this game, but I want to go beyond the kinematics. Going beyond the kinematics is trying to understand, what is your definition in your model of information of radiation? Maybe it's a question for Eugenio. I think Rob mentioned that, in ADCFT people have gone beyond, so maybe they have a deeper insight about what it is. But I think anybody that and the same thing for Pablo, like in his model, how would you encode radiation? And then, okay, gravitational, the Einstein's equations are some kind of balance equation between the amount of energy carried by gravitational radiation and somehow the memory that this gravitational does to the positions of the particle. That's really the essence of the gravity. So both of these concepts, let's say maybe the memory and the gravitational radiation, should have, what's your intuition about what it is from a quantum information theoretical perspective? Because without that, we cannot really quantize the Einstein equation. Both for who wants to start? Eugenio, Rob?
I can start. Yeah, so to understand the question is about radiation and information. And for finite regions of space-time, this is a difficult question. And I don't really have anything to add. I hope to hear something from Laurent later today. But for asymptotically flat spacetimes, there are results and still a lot to do. And I'm taking the same point of view that Carlo was taking of not information as foundation, but information as tool for doing calculations. So if you have a theory, and I can consider just semi-classical quantum gravity for the moment. We do have a notion of radiation. Classically, we do have a notion of the Hilbert space of gravitational perturbations at Scri plus. And now, what can information give us? What can we do with information as a tool? So there I have a comment. There I have a comment because we do have notions about the waveform or the energy carried by this radiation, both matter and gravitational wave radiation. we do have information, so this form that you can read, for instance, from the energy momentum tensor. But we also have a notion that is an information-theoretic notion ascribed plus. That is, and I'm going to try to characterize it in an operational way and not formal way. The operational way is, imagine that you have a detector far away. This detector collects radiation, and you can look at how much correlations is missing. And you can characterize that in terms of an entanglement entropy of the observables that the detector captures. Okay? So now this is a well-defined notion of entanglement entropy ascribed plus. It's not technically the entanglement entropy of radiation. It's really the entanglement entropy of all these asymptotic subalgebra up to a certain retarded time. So now you have two notions. One is the total flux up to a given time, energy flux. And the other is the total entropy up to a retarded time. And the question is there any relation between the two? A bit like we do in thermodynamics, where we say energy exchanges and entropy variation. A bit as Rob was saying, there's a first law of thermodynamics, but for entanglement. So the question here is there a first law for this kind of radiation? Now it's gravitational radiation from a black hole. And in a simplified case that you can think of as a spherically symmetric model, where you just consider as wave, some years ago, together with Mateusz Merlak, we found this exact out of equilibrium formula that relates energy flux and its time derivatives to this renormalized entanglement entropy of the subalgebra. And I expect that there's a generalization of that is in the full theory with asymptotically flat boundary conditions. There are lots of developments in this direction that are quantum field theory developments, but I don't know of semi-classical quantum gravity developments. And I find this interesting because I'm describing it as semi-classical quantum gravity, but it's using only notions ascribed plus. And so in a sense, you could even have a full quantum gravity in the bulk as long as you have a ascribed plus Hilbert space for all your modes. And so this is one connection that is specific enough that I see between information and radiation and energy, but it's in this logic of tool, not reconstructing the theory out of information, but using information to compute quantities.
Carlo, follow-up?
It's very much related. What I want to ask, this is a question that bothers me, and I don't have a perspective, and it's very much related. Rob and Eugenio have this fantastic result in this architectural space-time paper, in which if you look from a quantum gravity perspective, the possible states have all this different can be organized according to the way they are the different parts are entangled, and the states that correspond to a quantum field theory are this sort of intermediate thing in which you don't have you have the area law and the area law instead of the volume, etc., etc. And it's very much in the direction which goes around that that the structural spacetime is given by entanglement, which means that the notion of contiguity, being next to one another of two observables, it's related to the fact that there's an entanglement between the variable observed here and the variable observed next to it. But is it? That's my question. Or more precisely, yes, of course, there is entanglement between nearby regions in all states of quantum field theory. This is no decency. But are two observables adjacent to one another just because of that? Or there is a notion of adjacency that comes before of that, and then these contingencies on the sort of finite energy states of quantum field theory that since they are next to one another and since it's finite energy, it follows that they're entangled. So which way we have to think? And in quantum gravity, I think it's fundamental to understanding which way you have to think. Are nearby things entangled because they're close? Or to be close means nothing else that they're entangled? Do you have a view on this question? Or anybody has a view on this question?
Yeah, Rob, then Eugenio. Rob first.
Me first. Thank you. I mean, certainly in what we were doing, we were saying entanglement is a probe. It's something to characterize adjacency or smooth spacetimes. But it's very much in the spirit of what you were saying. We have some physics. We have these marvelous tools. You know, what can we do? What can we say about that? Since I have the microphone, I guess I'm supposed to respond over here as well, and I've forgotten what the question was. Something about radiation, yes. A lot of that gets swept under the rug for us because, you know, again, I was looking at anti-de Sitter space, and implicitly I was putting reflecting boundary conditions there, and so I think in a lot of the calculations I was doing, it's sort of, well, less important than, say, in asymptotically flat space. If I move to asymptotically flat space, there I don't have a really strong intuition about the gravitational sector. But, you know, I have been, well, holography, you know, there are all sorts of complications if I think about edge modes going implicitly in the background because what I'm talking about is a gauge theory already. And it's not quite the same, but what we found, or implicitly what we find there, is that it's you know, they are making a contribution, but for example, in these strongly coupled gauge theories, it's not a useful notion to sort of separate these are the edge mode contributions and this is the rest of the system. It's just, here is the total entropy, or here's the, you know, the quantity that we're looking at. And I can see that just because you can put asymptotically flat spaces in the boundary of ADS spacetime, you know, very similar ideas, or a very, perhaps I'm biased and I'm carrying that spirit into the calculations, but, you know, that experience with the gauge theory sector is really, yeah, I'm not sure what the role of the edge modes or what the importance there is. I will say to an even earlier question, you know, the idea of the constraint is an important one, and, you know, its role has to be understood, but it actually does make its appearance in new calculations that Witten, Pennington, and others are doing, well, Hong Lu, where to take, well, there's this fascinating work where in quantum field theory, you know, the algebras that people are talking about are type 3 algebras and everything diverges, you have no traces. But by properly thinking about the gravitational sector, you have to extend the Hilbert space, if you like, because of the constraint. And that actually has a major effect on the characteristic of, or on the nature of the algebra. And the claim is that it becomes a type 2 algebra where you do have a trace, and it's being applied in the context of a space-time with a horizon or a black hole. And so now I have a trace, and I can start talking about quantities like an entropy for the black hole, et cetera. So it's clear that it does play an important role, but well, again, in my mind, I'm you know, not adequately aware of what's going on, or I haven't digested fully what's going on, in part because papers haven't been published, and you know, so I don't have a full answer there on the importance of that. But Eugenio wants to respond.
I'm following up on Carlos' question. The question was, can we read neighborhoods of contiguity from the entanglement entropy from the area law? And my perspective is we do have a theory, consider for instance through quantum gravity, and in that theory you can compute all correlation functions of observables. So if you give me all correlation functions or observables in a state, I would claim yes, then you can identify continuity. There might be a superposition, so you can speak about expectation value and variances, and there might be states where continuity is well defined. But that you really need all these observables, all these correlation functions. So where does the entanglement entropy enter and how does it help? It enters because the entanglement entropy captures in one single number all of the correlation functions within one subalgebra. And so instead of giving a very large number of numbers of data or expectation values of these correlations, you just give one. And that's a mathematical statement that this gives an upper bound on some properties of correlation functions. And so in that sense, it becomes useful. You have one number that can tell you a lot, can give you a bound, and so in that sense becomes a probe. You don't have to control everything, you just control one quantity. I was phrasing it as identifying a corner or a portion of the Hilbert space where some properties arise. So this is the general statement. I would say it applies to any quantum theory, not just to quantum gravity or to quantum gravity. Then there's intuition that comes from cases that we have complete control of, and then one tries to export that from quantum field theory, from many-body systems. So there, let's take many-body systems, elementary quantum mechanics. There, if you have an Hamiltonian, and the Hamiltonian has a notion of locality, locality built into the Hamiltonian as first few neighbors interactions, and you look at low energy states, then you prove things like an area law for low energy states. And in quantum field theory, you can make similar arguments. And now there's the question about quantum gravity. And in quantum gravity, it is true we do have a more complicated dynamics. We don't have a standard Hamiltonian unless we have a special boundary conditions. But the Hamiltonian constraint is still a local object. The Einstein equations are still local and contain a finite number of derivatives. And so in that sense, you can still infer a notion of locality from this Hamiltonian constraint, except in the case of high curvature. So this is the observation I want to make. This is the addition to what I was saying before. The Hamiltonian constraint has this spatial part, this three-dimensional richest scalar part, but that part is present as long as you are in these smooth cases. But when you approach a singularity, that part becomes completely negligible, and it's the kinetic momentum square part that is dominating. I'm referring to the BKL conjecture at the classical level, and the idea that there should be a quantum version of all that. And so if you take that seriously, then these correlations are in the deep quantum regime, in the what we would call a cosmological singularity, should disappear dynamically. And so there you can still ask, is there still a notion of continuity? Because you don't have a reason to expect any entanglement between regions. And in that sense, I find interesting to go back again to my condensed matter colleagues and ask if there's a similar question there. And this is a well-studied question there. It's the issue of quantum quenches. You take a local Hamiltonian, you prepare the system in a completely factorized state with zero entanglement entropy everywhere, and you let it evolve, and you see what happens. And you see that you build an entanglement, and you can characterize how quickly you build it. And now there's something on trivia that is, if you factorize it completely, this is a state of high energy. Volume law states have high energy and are typical. Completely factorized states have also high energy and they are non-typical, and they're going to approach a typical state. They're going to explore your Hilbert space, and so you would have volume law. On the other hand, in cosmology, in this class of systems as the ones that Francesca and colleagues are studying, you have an additional ingredient. You have an expanding universe. So even if you started with a high energy density, because of the expanding part, this is going to dilute, and there's a chance that you are going from a zero law, not to a volume law and a completely out of equilibrium, out of low energy regime, but from a zero law to an area law. And that's something that I find exciting, and something that I see that could lead to signatures that you could read in correlation functions in the primordial universe.
We have a comment from Lee, and then we'll take a brief break after that.
I wonder if, and this is aimed at Eugenio and then everybody else, I wonder if there's a way to think about going from a world where space has not yet emerged, where everything is equally non-local, because everything interacts with everything else. And you somehow have emerged a structure which has lots of holes in it, has lots of correlations which remain off. And those are essentially what entanglement discusses. And so entanglement is the structure of who is correlated with who, in spite of the fact that they have no classical correlations between them.
Onyan, I haven't forgotten your question. We'll pick it up after the break. So let's take a 5-minute break and with other motivations.
Shall I ask my question?
Yes.
Okay, I wanted to kind of come back to this idea about information being fundamental, which was strongly suggested by Akim. And one thing I noticed in Akim's talk is that, I mean, after he outlined his vision of some potential way in which this idea could be realized, he came to this question, would we call that ultimately information? I mean, you arrive to this abstract space with these mathematical properties, and is this really information that we're talking about? And then there was Carlo, who said, you know, we have constraints. Constraints limit the number of possible states in the joint space versus the local ones, and there you go, you have information. But is this, I mean, which part of that is really about information? Why would we call these mathematical properties information? And I think intuition comes from the fact that quantum theory is probabilistic theory, right? And it's about probabilities, and it is because of that that we interpret these mathematical properties, or what arises in the case of constraints, as having to do with something that we call information. So I wanted to ask, otherwise, of course, we'll be just talking about geometry of projectors in some space. So when we interpret this as information, what is the intuition? Why do you think we're talking about information here? I guess this is a question to all the speakers and everybody.
Emily has a response. Up here in the front.
I just wanted to comment that this sort of discussion about whether information is just a tool or fundamental, to me, is irresistibly similar to sort of philosophical debates over structural realism, by which I mean there's sort of these two versions of structural realism, right? There's epistemic structural realism, which is the view that science largely tells us about structure and not about what instantiates that structure. So, and that to me looks quite similar to this view that information theory is valuable because we can use it without knowing exactly what instantiates it. And then there's this ontic version of structural realism, which is the view that ultimately only structure exists, and it corresponds, to me, it looks pretty similar to this view that information theory itself is fundamental and it's just information all the way down. So I think maybe there's something to be learned for this information debate from the long-standing philosophical debates over structural realism. And also, the point I would make is that perhaps in some sense it doesn't necessarily matter all that much whether you think information is truly fundamental or whether you think we're just using information theory as a way of characterizing the behavior of some ontology that we don't have a great handle on. Because, you know, either way, we can agree that as we go beyond these regimes that we can directly observe, increasingly it's structure and not an ontology itself that we have access to. And so it's kind of to be expected that in those sorts of regimes, information theory and other sort of structural tools will become increasingly important, and talking directly about ontology might become less important.
Akim and then Pablo, is that new or continuation? No problem, Akim.
Thank you. Right, so I like that point that the speaker before had, which is an attempt at the answer whether it's still information when we consider information theory to be really fundamental. And the argument, if I understood it correctly, was that yes, it should be, because what the correlators are about is probabilities. And probabilities have a natural information interpretation. I think that's a very good point. But then we have to ask, do we really have probabilities if all we are having at the lowest level of description, if what we have is these correlators, is it really probabilities already? Because probability is always, you know, the chance that something happens. And that requires events it requires the idea that there is a space-time, that events can happen, right? But while we still just have these correlators, without perhaps being even able to represent them as quantum field theoretical correlators on a curved space-time, maybe we are not yet justified to speak of probabilities even. Maybe these correlators are just pre-interpretable. They're just a mathematical structure at that point, and only in a regime where they can be represented as quantum field theoretical propagators on a curved space-time, then everything kicks in. Then we know we have events, we have probabilities, we have probabilities amplitudes, but before that, it's just a mathematical structure.
Pablo had a reaction, and then Carlo.
Okay. So I would like to react to this idea that information could be universal. Because as a computer scientist, whenever I studied information theory, etc., I never heard that information could be universal. The theorems about universality, they are about computation. Computation is universal, right? And computation processes information. Okay. So I guess the point here is, fine, you can work out correlators between the information that has been computed and then deduce how information propagated through the computation. But you still need some mechanism that processes the information. That's key. Also, there was this question by Laurent about trying to recover some dynamics, some gravitation, radiation. So I'm a bit clueless about that. Again, I'm a computer scientist, so I don't know, but I know how I don't want to do it. So the way I don't want to do it is by sticking there some Lagrangian in some Feynman path integral that does things that, okay, I don't know if it preserves probabilities or not. And there is also a good reason why I don't want to do it, which is that if you stick to unitary evolution, then you have something that you can compute. You have a computation over your quantum information. And in fact, you even have a quantum simulation algorithm for your theory. So I know maybe it's a bit early to say that, but perhaps in 10, 20 years, we can explore and quantum simulate some unitary dynamics for our spin networks and try and engineer, as we see it with our own eyes through these quantum simulated dynamics, try and engineer things that approach some Einstein field equations.
Carlo.
Since I'm here, just let me notice that the prehistory of QISS is a conversation between Pablo and Marius. So just you know that this exists because Pablo and Marius started chatting. Even before there was a quantum information, quantum gravity talking, but QISS really came out from that. I want to express my agreement strongly from the perspective of gravity. So general relativity, in fact, specifically, to what Akim and what Pablo have been saying. They both have been stressing that you need something on which to work informational notions, so to say, up to one point. Because Kim was speaking, I was thinking, yes, I agree, yes, I agree, yes, I agree. And then he said one sentence, said, whoop, no, I disagree here. So, so let me, and that's where you said, because we need, you were saying, the theory is strong enough to include quantum gravity. It has it's sufficient to have these correlators. They have to be about something. There have to be some event, right? And this event should happen, and we're talking about the probability of this event to happen. So we're talking about the event. And then you said, and of course, this event should live in space-time. Should be somewhere in space-time. And that's ambiguous. So it's because there are two ways of understanding this. It's the way we understood this phrase sort of before 1915, before everybody got convinced that 1915 was right, and after. Because before, the idea was that, well, there's a space-time there, so the event happened somewhere in this space-time. So the event has nothing to do by this space-time, except the fact that they are located somewhere in the space-time. But then there's general relativity. General relativity told us to think the world differently. Namely, the events are of the kind, a stone moving, but also sustained of the kind of gravitational wave moving, a black hole doing something. So they're not events in space-time, they're events of space-time. Space-time is so as such, they're not located somewhere. They define the location. It's the event itself that says, I'm this event, another this event, and they might be close or not close, but they're not in. So that's a crucial jump, which seems to me has nothing to do with quantum theory, nothing to do with information theory. It's just simply to do with general relativity. If we take general relativity seriously, the fundamental correlators you're talking about cannot be about in space-time there are events, but should be events out of which space-time comes out. That's what I was, the moment in which I said, well, wait a minute, it has to be interpreted in a relativistic sense. So they cannot be X and T labels. They can be something, they should be something else out of which the X and T label come out. Do you agree with this?
Yes, I completely agree. And I think your point about gravitational wave events, so to speak, for example, you could imagine having two gravitational waves meet and they are of such amplitude that they are getting into the nonlinear regime, so you have sort of events happening that are not just passing through each other. I agree, this is not just happening in space-time, it's happening to space-time, right? Yeah, absolutely. Beautiful point, yes. Thank you.
Follow up in the back table.
Yeah, sorry. I wanted to contribute to resonate with what Pablo was saying, to what Ognian was saying, and this discussion that we're having about information and, of course, now it's better? Yeah. Yeah, so I wanted to resonate to what Ognian, Pablo, and like what we have been talking about also, like Eugenio, on what is information a bit. Just a naive perspective from a PhD student. So Ognian said that information comes from probabilities, but I think that it comes from something much deeper than that. It comes from the counterfactual properties that we think that our systems can be in different states. And we think that because the structure that we are describing, we are not imposing some concrete dynamics. We think that we can have different dynamics. And this is related to the observable algebra. When we say that we have observable algebra, what we are essentially meaning is that we have some agency, that we can apply some different unitary and different computations from Pablo's perspective. So then like we could read and measure different things. So the notion of information, it's a counterfactual notion. So then linking to what Laurent was saying of how information can help us recover the concrete dynamics, we have to be very careful here, because the concrete dynamics can only be selected if from a structure where we pose that we can have different dynamics, because otherwise we would not have any notion of information. If we think that there would be like only one true dynamics, then the states would evolve like in a singular way, then you would not have any counterfactual notion, then you could not describe any notion of information, because you could not refer to what other state your system could have been in, because you think that essentially it can only be in one. So I think these are crucial distinctions that agglomerate all these sentiments of information distinguished from computation, and on the endeavor to find to recover the general relativistic concrete dynamics. But first, you have to describe the full space of possibilities, like of all the possible gravitational or quantum gravitational dynamics, in order to then pick out the exact Hamiltonian or action principle or whatever it would be that would correspond to the true dynamics that we observe.
Laurent had a follow-up. Up front, sorry.
Yeah, the follow-up to Pablo answer. I found Pablo answer very clarifying for somebody like me. That at least what I understand from Pablo's answer is that information is purely kinematical. So with only information, you cannot answer the question that Daniele is asking. But what Pablo is saying, okay, then what we should look for is some kind of computational principle, right? So in classical, we know that the principle is the principle of symmetry. So maybe there is maybe there's this kind of computational principle. And then maybe the question for people who are working in information, so is the notion of entropy or information really a useful concept to kind of design what is the best computational principle? I think that's maybe the more precise question that Daniele is asking, and I want to get the reaction to people who have thought about that, how they can use information somehow or this concept of entropy or certain informational tool to kind of help them think about, what is the right computation? Or what is, if you think that space-time is an agent making a computation, then, how is this agent arranging its gate according to what principle? Is it complexity? Is it something else?
Wenqing, you were next in the queue. Did you want to follow up on this or not? Different question. Then Lee and then Pablo.
There is only one universe. I think that's the first principle that we start with to do quantum cosmology or classical cosmology. There is only one universe. And I agree very much with the speaker who talked about what's possible. And let me make a second principle. If you're going to discuss in your physical theory an ensemble, it had better be a real ensemble that exists in the universe, in the one universe. There are theoretically many other possible universes, but there is just one universe in actuality. The others, this one somehow exists, the others do not exist. And this is how I and the people I work with have been approaching philosophy of cosmology, Roberto Manguiber, Unger, and other people. So don't talk to us about the ensemble of possible universes or possible versions of your system in the universe unless you believe that there is more than one universe or there are more than one member of your ensemble. And my sense is that if we start, these are basically the principles of relational physics. And if we start there, there's a lot that gets cut away. And we can start to do real, in my opinion, cosmology, whether classical or quantum. When we start with what's left, when we cut away all that, and I'm always frank, but I'll be even more frank, all this metaphysical fantasy or ontological fantasy of many universes, many degrees of freedom, etc., is what we're caught on, just like the people in the 16th and 17th century were caught on false metaphysical fantasies. So I'm sorry to put it so strongly, but I think that's the way it really is. And if you want to understand quantum foundation, let's understand it in a way that could apply to real systems in the one universe. Thank you.
Pablo?
Thanks. So I want to try and answer Laurent's question about whether tools like entropy, entanglement entropy, etc., can be guides to design the actual unitary dynamics computation thing that you want to put on your kinematics. And so I've been doing other things than this quantum gravity model. I've been looking at quantum simulation of quantum electrodynamics over cellular automata, over grids. And so what you have there is that if you create a fermion, then you need to create a whole gauge line. But this gauge line just goes in one direction. That's kind of weird, because you'd expect that the electromagnetic field induced by this fermion be sort of isotropic around. No? But of course, in a QFT, when they would create a fermion, they wouldn't do that. They would do a dressed fermion where they sort of homogenize the field around it. And then, I guess, if you were to look at how entanglement behaves, you'd recover things. I mean, I'm going a bit fast here, but you probably recover things like area laws, etc., only in this more typical stationary regime, right? And so also this goes back to Carlos' question. I mean, is entanglement related to geometry? Well, I would say, of course not. I mean, we have the Bell states, the EPR, the aspects experiments that really show entanglement at such a distance. So it's not, but it is in some kind of a typical low energy regime. So I guess the short answer is very much in line with what Eugenio answered earlier on, which is that I think entropy will help us design the dynamics, but only at typical low energy regimes.
Yeah, thanks, Pablo. This is very convincing. That what you're saying. I wanted to react to a comment by Nicedo, and which I thought was very good, and also Lee's reaction, and say a couple of things about that. Information is, way he put it, counterfactual, and in some sense probability it's as well. And he said, you even said it requires the notion of agency. I think there's some very good point here, but I think it's not in contradiction with what Lee was saying, that we live in a single universe. And I would rephrase it a little bit. This, I think, is crucial for the entire debate about quantum gravity. Information is modal. It's not necessarily counterfactual. Then whether you want to think about modality in terms of counterfactuals is your problem. It's which school of philosophy you belong to. I can think about modality without thinking about counterfactual, even without being David Lewis. I mean, this is the other way of thinking about modality. As a physicist, I don't even have to go very deep on that, because for me, laws of physics are regularities that I found by repeating many experiments and by using induction to think that these are what if I did it 5 times, it's enough for believing that it's going to be forever. So I assumed that I've made an infinite number of, this is induction, because I'm emphatic, I'm not sure, but that's what I do. But then I assume that there is a regularity here. And the regularity is that every time this starts, this follows. So the modality, which is deeply, and I want to insist on this, here you're completely right. Physics is model, okay? It's a phase space. If the initial state is that, then that follows. Physics is not about, this is a universe. It's never been like that. It's never been, not with Newton, not with Maxwell, not with Einstein, not with Schrödinger, not with quantum field theory. So physics is model. It's not a description of the universe. It's a description of, given something, what happened next. So it's an account we have found so far about regularity and things that happen because we have repeated many times and we bet that this is going to be regular. So every time we rethink, if you think about quantum gravity, how we describe how things are, I think we are lost because we are going out 4 centuries of successful way in which science works, physics works. We have to think gravity, quantum gravity, in the usual way. If this initial condition, whatever it means in the generalized sense in quantum gravity, what's going to happen next? So it doesn't necessarily to do with the entire universe, doesn't necessarily do with it's just, and because of that, yes, it's modeled, but agency has nothing to do with that. Okay, humans have nothing to do with that because there can be. The point is not if I intervene and I change something, what happened. The point is that well, if I happen to see different initial conditions, that's what happened. Okay, if the intervention has nothing to do with agency in the human sense, could be if a meteorite comes from the sky, it makes a big hole. The meteorite doesn't mean that if I throw down a meteorite, if I see a meteorite coming down. So this is what. Why also the correlators Akim is talking about play a role, because they capture, it's a way of capturing regularities and it's a model language for capturing them. And I think this is important in quantum gravity because what we want is not a picture of a description of how the universe is a description of the possible way in which it can be. In that sense, is it's, if you want to read it counterfactually, fine. But I think the proper way of quantum gravity to put it down to earth is that I have a phenomenon here. It's a quantum gravitational phenomenon. If I observe something, what am I going to observe next?
We have another follow-up in the center.
Yeah, so I just kind of wanted to, I guess, briefly try to respond a little bit to what Carlos is saying and what Nicetu said earlier, and I think Lee's comment as well. So if I've understood things roughly correctly, it seems like the state of affairs is sort of thusly. It's like, okay, our physical theories are capable of describing the world, right? If we have a deterministic physical theory, you might think of the Schrödinger equation as being a deterministic equation as well. Then that allows you to describe an individual world. Well, it allows you to describe many different individual worlds. And then when you're situated in the world, you have a problem of like locating which world you're actually located in. But you have some kind of, I'll use the word information at your disposal that is indicative of which of these worlds you're in that are capable of being described by your theory. And so it seems like when we start talking about certain kinds of probabilities, what we're really doing is we're sort of talking about encoding our uncertainty in which world we're actually locating into how we apply the theory. And this, I don't think necessarily has to be at odds with the idea of studying the whole universe in one shot, because you might think, for instance, of like quantum states. If we're just talking about pure quantum states, then the probabilities that come out of that are peculiar for a lot of reasons. But when we're talking about the probabilities that make states mixed, we usually think of that in terms of an ensemble. I'm sure Wayne would have a more nuanced view of this than I would. But if you have an ensemble, we typically think of those kinds of probabilities as, okay, I have literally lots and lots of instances of my system, and I want to study all of them. And that becomes really strange when we're talking about the full universe, because we do seem to only have one. But if you instead think of these probabilities more subjectively as kind of quantifying the limitations that I have on singling out which possible world is the actual world that really exists, then you don't necessarily need to be committed to the existence of all of these other worlds. You can just be talking about kind of studying all of these worlds all at once in a way such that you can remain as uncommitted as you need to which one is the actual one for as long as possible, or something to that effect. And so then, but how you actually carve this up in the first place to get these probabilities first relies on certain information that you already have. So there is something interesting. I don't think that information is, strictly speaking, something that you put on top of probabilities. I think you also can only start really writing down probabilities to begin with if you already have a bit of information somehow. So I don't know, that just to complicate everything, that I think is also relevant.
Onyan, was yours a follow-up or a new line?
Actually, it was not a follow-up to that, so maybe.
Okay, then I have a new line over here.
Okay, then maybe just to follow up on the previous comments.
So it is a follow-up. Go ahead.
Very quickly, I just wanted to kind of raise a sort of question. Like, again, we have physical laws and counterfactual thinking in classical mechanics as well, but somehow we don't seem much compelled to invoke the concept of information there. Whereas in quantum theory, we really feel forced because of its kind of fundamentally probabilistic nature, and I'm curious to know what you think about that fact.
Another follow-up.
Very quick. My dear friend Carlo, what you're talking about when you say what comes next is the time I believe in.
Eugenio?
So new topic, new question. It's really a question about quantum information and quantum gravity in a sense slightly different. So in the quantum information community, I understand that there's a significant effort in the study of superposition of causal orders. In the quantum gravity community, there's this non-trivial problem of studying superpositions of spacetimes with also superposition of causal structures that is going to arise. So my question is really how many of the tools from one community can be brought to the other? How close the two problems, the superposition of causal orders, for instance, in the quantum switch, are to the ones in gravitational path integral or in a spin form quantum gravity, or in other theories of quantum gravity with ADS boundary conditions, where one knows that this superposition of causal structures are going to be present. Do we expect constraints? Do we have an idea of how to detect this kind of phenomena? As Carlo was suggesting, we don't measure superpositions, we measure interference. What would be a signature of this phenomena for us in quantum gravity? And there's plenty of experts in the room, so I hope that many will comment.
Charles Love in the back.
Yeah, thank you for this question. What quantum information community can offer is exactly an unambiguous way of identifying something which would be, under inverted commas, superposition of causal order once the experimental data are there. But what is less clear how one can arrive in the experimental data. And so one way to quantify them is that you can, I mean, quantum information community also insists on operational things. That's not instrumentalism, it's just that we should stick to experimental data from which we make conclusions. And so the way how we identify superposition or indefinite causal order is that we look at all probability distributions that involve parties, can measure if there is a definite causal order. And that's more or less clear how to do it. You have Alice before Bob, before Charlie, you pick up all probability distribution, you see in which way signaling goes. And maybe it goes from A to B to C. And then we also say, good, sometimes maybe we even don't know which order it is. This is just a classical ignorance. Sometimes maybe there is a toss coin was tossed, and then you have ABC order and the other way BCA order. Or you simply don't know, maybe just one order was, but you don't know. And then we think about probability distribution that are classical convex mixture of these definite causal orders. And then what we call indefinite causal order, if this probability distribution cannot be understood as a convex mixture of this definite causal order, that's a very reasonable, I would say, very much in the spirit of a double-slit experiment, the probability distributions of interference not being the convex mixture of probabilities when you get that the particle goes only through one slit. What is less clear is how should we prepare maybe space-times in superposition in order to see these effects. And I think there is a mutual then kind of help that we can offer to each other.
Mariusz was next.
Thank you. Yes, I want to insist on this because I've already commented in another session, but I think there's still a bit of confusion. They do have a protocol to detect that there is a superposition of causal orders in the quantum gravity sense. It's not feasible. It's a Gedanken experiment. It would take whatever, 10 to the 5 times the lifetime of the universe from a back of the envelope calculation, but they do have a Gedanken protocol for this. It's a gravitational quantum switch. There is another nice paper by Marko Vojinovic where they discuss this. The crucial element is that you need to have a one use of the operation. Operationally, you can do this by what I was saying last time, to just allow this operation to be available for only one instant of time. So when you were saying, both you and Carlo, you need to use interference and everything, they have this. And the trick is to accomplish a task, to say whether two unitaries commute or anti-commute, at a single shot, essentially, which is impossible to do classically. So they have this protocol, which is something in addition to what we have in quantum gravity, in the sense that in spin forms there's going to be all sorts of superpositions, and even, I think, cases from your paper with Pierre, where you cannot even speak about causal order to begin with. But there is, to my knowledge at least, no way, nobody has discussed in loop quantum gravity how you would actually witness this, right, experimentally. So this is something they do have, and I think this has gone somehow unnoticed because, as we were saying last time, they are setting a higher bar of what it means to actually witness something. But I think for the standards used in loop quantum gravity, they totally have a protocol that would verify this. It's Gedanken, and one question is, could something more feasible be thought of? I think it's a very interesting question. I'm not sure what that would be, though.
Carlo is next.
I'm very happy of this exchange, and in fact, it was very clarifying to me. And thank you, Eugenio, for putting it so clearly, the question, and thank you, Czesla, for because I was always confused by this quantum superposition of causal structure. I never understood exactly what it meant. It seemed to, on the one hand, to be complicated, on the one hand, to be trivial, and I think that this way of formulating the question, what is the in the final probability that you measure, the signature that you read out, it's and I think you agreed contrarily that this is the way. And the reason I got confused is because of exactly of the quantum switch, because it sort of came out as an example of superposition of causal structure, but then you can do it in the laboratory and measure exactly those quantities, and so that obviously is not anything funny going on. It's not just the standard quantum mechanical stuff that two different branches is interference and two things happen and you cannot put them together. And it's the fact that in one thing what you call A happens before or after what you call B is just standard quantum mechanics. So do I understand correctly that the quantum switch, including your version, the one with the mass that moves around, does not yet satisfy the condition of characterizing a set of probabilities, measured probabilities that detect a quantum superposition of causal structure, or am I wrong here?
Yeah, there is, as I defined what be operational way of detecting the causal, indefinite causal order, indeed, it can be done also in the lab. And then the photon that experiences operation on it will be in what we say indefinite causal structure. Full stop. The only difference with the gravitational quantum switch is that not only photon, but many systems around that, and the whole space-time will be in the superposition, and though many systems moving in this system will be in this structure or configuration, will undergo indefinite causal structure. And the universality of the fact that in gravitational quantum switch, the system will undergo the indefinite causal structure tells you that it is a superpositional space-time, and that's the difference between the previous case. It can be also refined more. But I just want to say that we, in this whole field, and maybe Ogden wants to add something, we have also indefinite causal structure that do not appear to be superposition of classical space-times, if you want. We have structures, and Emily was talking about that in her talk, things that we can prove within the, let's say, process matrix formalism, that they obey indefinite causal structure and very strongly obey, namely what we call in theory independent way. We have something which is very analog to Bell's inequalities, which we call causal inequalities, and then independently what the theory behind that, future or current quantum gravity theories, we will be able to test whether they allow, in that very strong sense, non-causality. But however, all what we have tried, even with the gravitational quantum switch and superposition of space-times, or in general, we call this quantum coherent control of circuits, do not, and it probably cannot violate those. Ogden has maybe a different opinion. But there, nevertheless, in the process matrix formalism, there are some structures that can violate them. Now, unfortunately, those that can violate, we don't know how to implement, and those for which we know how to implement, they do not violate. And so one thing of understanding this, and I think Emily was mentioning this, is some kind of a good causal loops that never bring you into the grandfather paradox. So these are some causal loops where you send information to the past of the other observer, and the other observer sends information to the past to the yet another observer. And in a tricky sense, it's a causal loop, but a causal loop that never allows to send the information back into your own past, which will be the grandfather paradox. And this is very consistent in our framework. We can even have this understanding of some kind of causal loops, but we don't know how to implement this. And I think, for example, a great research project will be to see if and this have nothing to do really with the quantum physics, it's just more a topological thing. Whether GR allows such solutions, in a sense that we know that GR allows solutions of causal loops, but you don't want those because they can produce grandfather paradoxes. Whether GR allows solutions that exactly mimic situation in which you have a strange topology, but you never send information to your own past.
That would be super interesting, and I very much look forward for this clarification. As a side remark, I think that GR admits solutions with closed causal time-like curves, and I don't believe that there is anything paradoxical about them. I think that the so-called grandfather paradoxes follow from assumptions about freedom that once you try to stick into that particular geometry don't follow because of entropy, because of all sorts of stuff.
I'm just referring to this. So it will be a paradox once you have a freedom of choice to do as an observer. And I want to say, and this is very important, the process matrix formalism allows the freedom, absolute freedom of choice. And that's why, nevertheless, you see a non-trivial topology or non-trivial causal structure that avoid any paradoxes under the free choice. And nevertheless, it's not a linear time.
Yeah, I got this point. The distinction is clear. Yeah, thanks. Yeah.
Finching, yours was a follow-up? Is that right? Up front here.
Thank you. I will comment on Eugenio's question first, then I have a separate question. So this indefinite causal order in quantum information sense is actually completely different than in the relativistic sense. And so in quantum information, it's in terms of the local operation relative to some reference frame, and for the relativist, and the indefinite causal order there does not violate anything about the macro-causality that we're usually familiar with. And so actually it's a huge challenge to fluently translate between these two pictures in order to help our understanding of the causal structure in quantum gravity. And then I have a completely different question, but we can come back to this causal structure later. This is also related to yesterday morning's section. So it's that when we are using quantum information tools, we are also assuming all the fundamental principles from the quantum physics. And traditionally in quantum gravity, we have been, in different approaches, we tried really hard on quantizing gravity, but there has been less efforts on thinking about what quantum physics, I mean, generally including field theory, need to modify in order to have the quantum gravity. So I'm wondering whether this quantum information in quantum gravity can be a great opportunity for us because we are pushing the principle of quantum physics to the extreme to tell us something about the foundation of quantum physics that need to be changed in order to have quantum gravity. And I would like to hear experts' wisdom on the strategy of this question. And I already know that Carlo will say, no, we don't need that.
Oh, yeah. In the back.
Okay, I will kind of first comment on the first part of Lynchian's comment and Eugenio's general question. I think that she made a good point, but then I'm going to jump over her second question and come back to comment further on Chasta's response and the discussion about the gravitational switch and all of that. So first of all, I think it's a great question, this really bringing together these two very different, bringing these concepts developed totally in this kind of framework of operational hypothetical experiments, on the one hand, and on the other hand, really kind of quantum gravity theories, specific proposals and models for how quantum gravity works. And what Lynchian said is very important is indeed this fact that in these operational frameworks in which these concepts of indefinite causal order have been formulated and defined, you think about local operations. So this is kind of a starting point. They are local in a certain sense that need not be local necessarily in space-time, but in the original way we conceive them, we imagined them to be local in space-time. And when one tries to establish this connection with, let's say, more first principles theories or some approximate theories of quantum gravity, the challenge that one sees is that usually the way people do quantum field theory, high energy physics, it's not based on local operations. It's not expressed in terms of, at least in an obvious way in terms of correlations between experiments. Usually you talk about probabilities. There are correlations, but usually in a sort of scattering type of experiments, or it is difficult to establish the connection to these areas where you have various parties performing local operations in space-time. So, for instance, one uses correlators in quantum field theory, but these are not necessarily immediately clearly how they relate to actually correlations between local experiments. And one needs to do some work for actually translating these very strongly developed concepts in high energy physics to this. I do not think this is really like a fundamentally difficult problem, but there is this gap that needs to be crossed in order to be able to speak the same language and properly address. And then I think this is a very interesting program. It's one thing we are attempting to do, but for instance in our group, but it's still at early stages. Whereas now when it comes to the discussion about the gravitational switch versus the other type of switches that people have done, I just want to comment. I do have a potentially slightly different way of expressing these connections than Časlav, maybe complementary in a way. So Časlav spoke about how in the laboratory the photon or some aspects of the photon have something like indefinite causal order or causal structure, but like in the gravitational field, this is a more universal because everything around the local experiments experiences the same kind of time dilation. I think that to be more precise, to precisely understand the sense in which these laboratory experiments realize the theoretical concept quantum switch, one needs to carefully identify which physical degrees of freedom corresponds to the mathematical objects. And like, for this purpose, I've introduced this concept of time-delocalized systems or time-delocalized algebras, which provides precisely a way of interpreting or saying which are the degrees of freedom in that experiment that correspond to Alice, that correspond to Bob. And when one analyzes this carefully, one sees that it's slightly different than the naive, kind of intuitive way of understanding this, like is the internal degrees of freedom that experience this operation at some sort of indefinite time. Truly what experiences this, what is happening is that what is in indefinite causal order are certain operations, but these operations, they are delocalized in the space-time in a way that not only delocalized in time over the Hilbert space, let's say, of the target system of this that passes through this experiment, but also over the control qubit that is there. So it's a non-trivial way of actually mapping the theoretical concept to the experiment. And what I want to stress there is that I believe the precise conclusion should be that you can say this is a realization of the theoretical concept, but the relata that are can be said to have these indefinite causal relations, or more precisely, one can describe them in terms of cyclic causal relations. They are these time-delocalized algebras, observables, or time-delocalized systems. But within that same framework, we have recently also shown that there are processes that violate causal inequalities that do have realizations in that sense, also in the laboratory. So in a time-delocalized sense, in that particular sense, which I believe is one way of precisely saying how that is an implementation of the concept, we have shown that there are processes that violate causal inequalities also existing in that sense. But this is different. Now the relata are different. They are not local in space-time, and the natural question is whether these systems could be seen as local in with respect to some reference frame for space-time, which is somehow quantum, or that could a situation that could arise in a quantum gravitational regime.
All right, we have one final follow-up from Pierre. Please keep us localized in time, Pierre.
Yeah, I just wanted to stress that indeed I think there's really a difference of conception of causality between the two communities of quantum foundations on the one hand, quantum gravity on the one hand, on the other hand. And so when people talk about a superposition of causal order, they mean actually, I think, different things. Like on the one hand, in quantum foundations, you have a very operational way of defining what this means, and you're considering local labs which can actually perform some experiments, and then from that you're deriving causal inequalities, and that would be the signature of superposition of causal order. On the other hand, in quantum gravity, we do not have this operational way of defining things, and we are only dealing with a gravitational field only, and in that context, we have notion of causality which is really tied to the gravitational field and what it means to have light cones locally. But I think that in that context of gravitational, in quantum gravity, there is a way also to test whether we do have this superposition of causal order, and that would be if we manage to make a measurement for the probability of transition from one space structure to another space structure, and if we are able to measure this amplitude and then to compare it with the computation of the transition amplitude, then in that case we would have an indirect way to see whether the contributions within the transition, there are contributions which encode a non-causal structure inside, and these contributions, they would contribute to the final computation of the amplitude. And so that would be a way, I think, to see concretely that we have indefinite causal order in quantum gravity as well.
And with that, I'd like to close our session. I want to thank the Igniters and all of you.
Thank you so much, Hal, for the magistral